However, you have the possibility of having, if you think of the statistical manifold as being an arbitrary subset of this object here, then you have the possibility of having statistical manifolds with much more interesting topologies, which are always surprising, and you have a number of statistical statements that you can make on manifolds that are not trivially topological. Now, this statistical manifold let me try to elucidate here what are the symmetries of the statistical manifold. Of course, as a statistical manifold, as a manifold, it has you have to require that two manifolds are the same regardless of the coordinate system that you put in there. So you require general covariance, and you also have to require invariance under choices of distributions that define the densities. Many times you describe the statistical model with densities, right? Densities are arbitrarily chosen. It depends on an underlying measure for defining densities. Well, in order to, if you have two choices of density, of underlying measures, you should have exactly the same statistical manifold. Well, there's one more invariance that hasn't been really completely exploited, and which is the most characteristic invariance of statistics, which is what I call a sufficient map. This was discovered in a special case by Fisher, of course, and it's basically a new notion of invertible map. I mean, if you can map, you have a one-to-one correspondence between one manifold and the other. Of course, it doesn't matter whether you use this or the other. They should be taken as equivalent. Here in statistics, you have a new way of a new equivalence, a new invariance, which is a sufficiency map, which means that remember that the data theory is always a two-sided object. X, which is the observable part, and P, which is the hidden part, that goes together. But I can make a map between an XP and another YQ. Now here, dimension doesn't matter, because you can throw away superfluous stuff. In other words, I call a transformation from one S to another sufficient if I can recover an X prime equivalent to X, basically having the same hidden part as X itself, just by knowing Y here. That's what I call a sufficient map. I can always recover the original data equivalent to that, that is coming from the same hidden part as the other. Well, that's a sufficient map. In fact, you can show this is equivalent to say that X conditional on Y is independent of P. That's the regular definition of sufficiency. Let me give you a concrete example. Here's the canonical example. Suppose that you have n independent observations from a standard Gaussian distribution. You don't know which Gaussian, like that. So you have 1,000 numbers, okay, that they are coming from some Gaussian that you don't know which Gaussian. Well, okay, now, if the model is true, if in fact you have, the data is coming from a Gaussian distribution, and they are independent, you can throw away everything except two numbers. Keep just two numbers. Just take the average, the observed average, and the observed standard deviation, and then modify the probabilities here as being just this particular Gaussian. That's the distribution of X bar, you see, and they have to be independent in this case. And this thing here, sigma squared over n times the high square n minus 1 degrees of freedom. That's standard stuff from sampling theory. Well, this manifold here that has n plus 2 dimensions, and that manifold there that has only 4 dimensions are completely equivalent informationally. They're exactly the same thing. So this gives birth to a new kind of sort of topology here. See, when you have two manifolds, you say they are topologically equivalent if there is a deformation of one into the other. Now, that preserves dimension. This thing here doesn't. Dimension is a much more softer thing than in topology that becomes an invariant. Here, dimension is not an invariant anymore. But there's a bigger consequence of realizing what the symmetries of statistics are, and that is that one can show completely, at least for bigness, which is in a sense, you can approximate anything with that, you can show that the only scalar functions of two elements in here, that positive scalar functions of two elements that preserve this invariance of sufficiency are a one-dimensional collection of this i's of deltas where delta varies between 0 and 1. And these are the only scalar functions that are invariant under sufficient transformations. That mean that preserve the main symmetry of information and statistics. That this is the family of delta information deviations, and all of them, if you look at very close points here or there or anywhere, if you look at it to close points, they give birth to exactly the same Riemannian metric Fisher information. In fact, we should say Fisher information is nothing but the metric induced on your model by the Hellinger distance outside. Okay, here is a very concrete example that was discovered by my former PhD advisor. This is what I call Herbert Robbins' gospel, the gospel according to Robbins. Let's forget about all this generalities. I'm going to make it very, very concrete for you. I'm the owner of an insurance company. Okay? I want to insure you for your accidents, and if you, I want to charge you if your proneness to accidents is big, I want to charge you a big insurance. If you never have an accident, then it's cheap insurance. Now, suppose that you model the data like this. This is the first driver. This is the number of accidents previous year. You can have 0 accidents or 1 accident, so 0, 1, 2, so on. Those are the x's. Now this is my other driver, and so on. I have n of them. Now attached to these drivers, I have this impalpable, unobservable proneness to accident. Okay? And I model the data by saying these n vectors are independent, identically distributed as one x theta the distribution of which is given by the probability of x given theta. It's just a regular Poisson with mean theta. And theta, I assume it has a distribution, but I claim that I don't know what it is. It could be anything. In fact, it doesn't even have to have a density. Any distribution whatsoever. Now here's the magic. Now, the x's are independent and the thetas. You may say, well, if I want to estimate the proneness of accidents to in driver number 1, I assume that completely independent of this. If you have independent parts, then it doesn't matter whether you do them separate or together. Wrong. It matters a lot here. You can do much better. This has been tremendous discovery in statistics that in dimension 3 or higher, it matters. This is due to the fact that there are no superharmonic, positive superharmonic functions in dimension 3 or higher. There are plenty of them in dimension 1 and 2. So in dimension 3 or higher, combining independent problems, if you have to estimate the 3 of them, or more of them, it makes a big difference whether you put them together or you collect them separately. In other words, if you have to estimate the temperature in Alpha Centauri and the stock market in Japan and whatever the speed of something here, and you have to estimate those 3 things, then you do better by combining them, even though they are completely independent, than they do it separately. This is a mathematical fact. So therefore that axiom goes. It's not true. Well, the nice thing about this example here is that, here's the magic. With that assumption that the xi's, theta i's, they're independent, you just marginalize the x's and you can see that then the thetas have to be independent, coming from the same distribution that you claim that you don't know. There's any g whatsoever. Now, if you marginalize the thetas, then you see that the x's themselves are also IID coming from the marginal distribution of the x's that includes g there as a mixture here. Well, the thetas are impalpable, but they leave a dent on the x's. In other words, in such a way that by the law of large numbers, you can estimate the probabilities here. Almost surely, when it is large, you see the observed number of drivers that have zero accidents, the proportion of drivers with zero accidents will estimate f sub g sub 0 here, and so for every x. Therefore, you can estimate the Bayesian estimator of theta with, if you can estimate this f g x, you can estimate the expected value of theta given x, and therefore, just by what? By looking at just replace here this fg by its own estimator, fn, and the fg here, that it happens to, this is just a one line, this statement here follows directly from the assumption that the probability of x given theta is Poisson. Just write it down, you see that happens to be like that. And therefore, this was proven in the 1950s by a student of Robbins, dotted all the i's that if n is sufficiently large, then you can estimate the thetas as well as if you knew g itself. Therefore, in other words, you just use the empirical distribution. All this stuff here on the left is observable, and if n is sufficiently large, by the Glevenko-Cantelli lemma, or Glevenko-Cantelli theorem actually, the empirical distribution will be a strong uniform approximation of the whole distribution function of the thetas. Well, that either you're a subjective Bayesian or you understand this, mutually exclusive or. In other words, you can put any prior you want or assume you're any prior you want, but if you have sufficient data, the data is able to estimate the prior. And you don't make any assumptions on the prior whatsoever. You don't have to believe me. By the way, do not believe me. Just go check it out. This is a mathematical fact. It only says that A equals A. Alright, now this is a preview of my talk on Friday. I'm going to give you a concrete example, very trivial, of proving that why the frequentists here that come from the temples of Berkeley, it's not that, this is just a cartoon, of course. Yeah, I'm saying that this is, not right now, there is a big divide here. Frequentists, that they use the maximum likelihood estimator and find things when it goes to infinity. And then you have here the Bayesians, the churches of England here, where they you just know what that is, right? Okay. Well, Jeffrey got it wrong. I mean, we're all here following the Jeffrey's recipes and the sigma over sigma and all this. I'm going to show you that doesn't work. It's not right. It's not right when the volume, the information volume of your model is infinite, or that means when this is going to integrate to finite, then it's wrong. Jeffries, as Ariel said, maybe saying it. In fact, I was confused for a long time. I always thought that Jeffries had understood this because he used the right notation. If you look at the Jeffries book, he used G mu nu. So I said, well, he understands what he's talking about. But then you keep reading, and then you realize that he didn't. That maybe being at Cambridge, Eddington was around there, somebody, he knew about Einstein's general relativity, but he didn't understand. Because as soon as his Jeffrey's prior didn't work, he said, well, sometimes it works, sometimes it doesn't. For example, for